Additional gas law is what we're going to cover in this lesson, and obviously that implies we covered several in the last lesson, and we covered the ideal gas law in the last lesson and all the individual gas laws leading up to it. Now, in this one, we're going to bookend it with two new gas laws, and the first one's going to be Dalton's law of partial pressures, and then we'll finish it off with Graham's law of effusion, and then in the middle of that, we'll talk about STP and the molar volume of a gas at STP, standard temperature and pressure, and then we'll talk about a relation between gas density and the molar mass of a gas as well. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, in addition to high school and college science prep, we also do DAT, MCAT, and OAT prep as well. You can find those courses at chadsprep.com. Now, this lesson's part of my new general chemistry playlist. I'm releasing several lessons a week, covering an entire year of general chemistry. I'll be doing this throughout the school year, so if you want to be notified every time I post a new lesson, subscribe to the channel, click the bell notification. So let's start this off with Dalton's law of partial pressures. And Dalton's law, simply put, says that the total pressure when you've got multiple gases inside a container is just going to be the sum of the individual partial pressures of those individual gases. And essentially what Dalton really said here is that each gas is responsible for a part of the pressure. So, and it turns out the only thing that really matters is how much of that gas you have relative to everything else. And so we'll end up talking about what's called the mole fraction, which is just the fraction of the total moles that a particular gas is responsible for. So, but rather than introduce this with, an equation, let's just talk about this rationally for a second. So it turns out that most of a gas, under most conditions, is made up of mostly empty space. It doesn't matter how big or small the molecules are. And so whether we're comparing N2 to O2 to CO2, the size of the molecules largely is not going to matter under most conditions we look at. And so what Dalton really said then is that every gas has a chance to contribute equally to the pressure, just dependent upon how much you have. But if you had equal amounts of, two different gases, they would contribute equally to the overall total pressure. Now, if we take a look at what we've got here, we've got 10 moles of N2, 8 moles of O2, 2 moles of CO2. If you look at this, we've got 10 out of a total of 20 moles are N2. That's half the moles. We'd call that a mole fraction of half. And ultimately, what Dalton's law of partial pressures leads us to believe then is that if half the moles are N2, well, then he's responsible for half the pressure, and half of that pressure of 50 atmospheres total would be 25 atmospheres. Now, same thing for O2. So here O2 is responsible for 8 out of 20 of the moles. So therefore, he's responsible for 8 out of, 8/20ths, if you will, of the pressure. Well, 8/20ths is 4/10, that's 40%. And in this case, 40% of that 50 atmospheres is going to come out to, in this case, 20 atmospheres. So we figured out that N2 is responsible for 25 of the atmospheres, O2 for 20 of the atmospheres. Well, then the rest must be, CO2's responsibility, and that's going to be an additional 5 atmospheres. But we could once again say, well, he's 2 out of a total of 20 of the moles of gas. That's 1/10 or 10%, and 10% of 50 atmospheres would be 5 atmospheres, just like we concluded. So that's kind of how this works. So Dalton's law formally says, the total pressure is just equal to the sum of the individual partial pressures. Well, in our case, instead of just leaving this, generic with A, B, and C here, we can put in our individual gases for this particular problem. We want to find the individual partial pressures for all of these in this system. So we're going to have N2, O2, and CO2. In our case, that's going to add up to a total of 50 atmospheres. Now, if we want to find one of their individual partial pressures, so in this case, let's say we start with N2. We would take the mole fraction, again, which is just the fraction of the moles in this case that are N2. And in this example, that's 10 out of a total of 20 are N2, 10 out of the total of 20, sum them all up. And then we'll multiply that by the total pressure given of 50 atmospheres. And so that partial pressure of N2, again, 10/20 is 1/2, and half of 50 is, again, 25 atmospheres. We can do the same thing for the O2. Notice we're really just doing what we already stated in words. I just want to state it, make it make logical sense, because if it makes sense to you how it works, then you don't actually have to memorize an equation. You're like, oh, well, N2 is half the moles. Well, it's half the pressure as well. All right, so in this case, O2's mole fraction is 8 out of 20 times that total pressure of 50 atmospheres. And again, that's going to come out to 20 atmospheres. And then for the partial pressure of CO2, we could do the same process, or we could just say, well, whatever it is, they all have to add up to a total of 50 atmospheres. So we could fill that in and be like, well, 25 plus 20 plus another 5 adds up to 50, so it must be 5. So the last one you can kind of deduce to get that total. Or again, you could do the same process here, and in this case, CO2 is responsible for 2 out of 20 of the moles of gas. Again, times 50 atmospheres is going to get you that 5 atmospheres. Cool, and that's really all there is to Dalton's law of partial pressures. You got to know the sum of all the individual partial pressures adds up to the total, but then you also got to know that to find that individual partial pressure, it's just the mole fraction of that species times that total pressure. So now we're going to talk about the molar volume of a gas at STP. And so first got to talk about what STP means. And so STP is short for standard temperature and pressure. And that corresponds specifically to a temperature of 273 Kelvin, aka 0 degrees Celsius, and a pressure of 1 atmosphere. So definitely got to know what STP represents. And then you're supposed to know that, just a fun fact to memorize, that 1 mole of a gas at STP, that's behaving ideally, will have a volume of 22.4 liters. And that comes right off the ideal gas law. So if we take PV equals nRT and rearrange this to solve for V, so if you plug in 1 mole for N, plug in the gas constant of 0.08206, plug in a temperature of 273 and a pressure of 1 atm, when you solve for V, it would come out to 22.4 liters. And it wouldn't matter what that gas is. And so if you've got 1 mole of gas at STP, volume's 22.4 liters. If you have half a mole of gas at STP, the volume's going to be half of that, 11.2 liters. If you have the volume of 10 moles of gas at STP, then the volume would be 224 liters, 10 times that number. And so STP just shows up so commonly that it is convenient to remember the volume of, per mole of gas. And this might come in handy in like a stoichiometry type context. So that's a example we're going to look at here. And so here we've got magnesium plus hydrochloric acid producing H2 gas and MgCl2. And so the question we're going to ask here is that if we've got 48.6 grams of magnesium reacting with excess HCl, so that's your key that the magnesium is the limiting reagent, and it's reacting to completion, what volume of H2 gas at STP is produced? And so in this case, we wanted to calculate a volume of H2 produced. And to figure that out, we'd actually have to figure out the number of moles of gas produced first. And what you really do is just look at, well, if he's limiting reagent, well, we've got a 1-to-1 ratio, and, that's your mole to mole ratio, and just treat it like a regular stoichiometry problem. And once you figured out the moles, instead of converting it to like grams like we might do in the past or something like this, now they want us to convert it into a volume, and you'd use the ideal gas law to accomplish that most of the time. However, if specifically they ask you what volumes produced at STP, which is the most common conditions, well, then you don't actually have to use this. You can just take advantage of the fact that for every mole of gas you do have, it occupies a volume of 22.4 liters, and you can just treat it as part of the stoichiometry dimensional analysis calculation. So let's take a look at how this works. So in this case, we'll take, and first, to relate our moles of magnesium to moles of H2 and take advantage of that 1-to-1 ratio, well, we first got to turn the magnesium into moles here. And so in this case, 1 mole of magnesium is 24.3 grams. I made the math nice here so you can kind of see that we've got exactly 2 moles, it turns out. And then we'll use our mole to mole ratio here, and that's the ratio of moles of H2 to moles of magnesium. It's just the coefficients of the balanced reaction, again, you might recall, for that mole to mole ratio. And now we could take that, we could stop here and just calculate out that moles of H2 and then plug that in for N, again, right here into our ideal gas law to solve for the volume. And if we weren't at STP, that's exactly what I'd recommend you do. But at STP, you can now just go and say, well, 1 mole of any gas, including H2, has a volume of 22.4 liters. And again, the only reason we can do this is because they told us we're at STP. And so it's just one further calculation. And now we'll pull out a calculator. In fact, you can probably do this without the calculator, but we'll need that later anyways. So, but again, 48.6 divided by 24.3 is 2 moles of magnesium. And based on the 1-to-1 ratio, that should produce 2 moles of hydrogen. So, and then again, if we got 2 moles of hydrogen, well, if each mole is 22.4 liters, then 2 moles would come out to 44.8 liters. And again, had you just, got all the way here to 2 moles and then just plug that 2 in for N into the ideal gas law, you'd get the same answer. But again, here's a faster way to do it. And again, the only reason this is useful is because the most common conditions you might be asked such a question are the conditions of STP. So now we've got to talk about gas density. And so it turns out density, the definition hasn't changed. So density is still mass divided by volume. But it turns out specifically for an ideal gas, you can actually put a different expression on it where it's pressure times the molar mass of that gas over RT. And it turns out this actually is still equal to mass over volume, which is density. So you may or may not be provided with this equation, so some of you may have to memorize it if you want to use it, or just get around using it, as the case may be, as we'll see. But basically, you can kind of look, if we take a look at the ideal gas law here, PV equals nRT, we don't really have mass as a part of this, but we do know how to turn moles into grams back from our stoichiometry chapter, so we could get something similar to it. So what I'm going to do is rearrange this here and bring V over, and we're going to get N over V equals 2, and then we'll bring the RT over to the other side, so it'd be P over RT. Now this is not the same thing as density though, because again, density is mass over volume, not moles over volume, but you do know how to convert moles into grams. And to convert moles into grams, you just multiply by the molar mass. And so I'm going to multiply this side by the molar mass, capital M there. So however, if I multiply that side by the molar mass, well then these aren't equal anymore, and so I've got to multiply this side by the molar mass as well. And if we do so now, again, moles times molar mass equals just plain old mass, which means this is mass over volume, and this is density. And so we've essentially just derived the other expression here for the density of an ideal gas. So pressure times molar mass over RT, and so there's only 3 variables you've got to know to calculate the density of a gas. Now again, if you know its mass and its volume, well great, just use M over V. But more than likely, you're probably going to be given terms of pressure and temperature, and then have to look at the periodic table to get its molar mass, and you could still calculate the density there as well. So let's take a look at a question here. So what is the density of helium gas at a pressure of 2 atmospheres and a temperature of 273 Kelvin? So not at STP exactly, so standard temperature, but not the standard pressure. And we want to know what's the density. Well, okay, we could take this approach, and if you know the equation, well, then it's going to just be plug and chug. And in this case, we just plug in that 2.0 atmospheres. We look at the periodic table. So in the molar mass for helium is 4.0 grams per mole. So actually, I'm just going to round it to 4 to the nearest whole number for the molar mass there. And then all over RT, so we got 0.08206 liter atmospheres per mole Kelvin, and that temperature of 273 Kelvin, and we could get that density. So let's do that here real quick. And 2 times 4 divided by 0.08206 times 273, denominator all in parentheses, and we're going to get 0.357. And this is going to have units if we take a look here. So we'll cancel out the atmospheres here, we'll cancel out the moles here, the Kelvin here, and it's going to be grams per liter. And once again, that's a rather low density. If you compare that to, say, water, well, water is 1 gram per milliliter, which means it would be 1,000 grams per liter. And so, again, but gases are made up mostly empty space. Molecules are much more spread out than, say, in a liquid or a solid. So it's not surprising that the density of a gas here is much less than, say, liquid water. Cool. Now, another approach you could take to this, if you didn't have this formula, then you might just get around it. So you do need to remember one thing, is that density is an intensive property. It doesn't matter what sample size you have. And so what you could do is just say, well, you know what, I'm going to just calculate the mass over the volume. So, but you've got to choose your sample size, and I think it's really convenient to choose a 1 mole sample size. And so if we have 1 mole of helium, Well, look at the periodic table, and 1 mole, that's, going to be the corresponding to a mass that's the same as the molar mass. And so for our mass, we just get our 4 grams. But then for our volume, that's what you're going to use the ideal gas law for. Notice again, we derived this using the ideal gas law. And so in our case, we take our volume equals nRT over P, which in our case, we decided to use a 1 mole sample size times 0.08206. Getting ahead of myself there. Liter atmospheres per mole Kelvin. And then temperature of 273. All over pressure of 2 atmospheres. And so in this case, 0.08206 times 273 divided by 2 gets us 11.2 liters. And we just take and now make that our volume here of 11.2 liters. And if we take 4 divided by that 11.2, we're going to get 0.357 grams per liter yet again. So multiple ways to skin a cat. If you don't, know this equation, it's not provided for you on like an equation sheet and you don't want to memorize it, you by all means don't actually have to use it. So, but you've got to basically take your moles, and you typically are going to choose the sample size because it's intensive and it doesn't matter what sample size you choose. And you're going to have to take that number of moles and convert it into a mass using the molar mass of that substance, and then also turn it into a volume using the ideal gas law. So the last topic in this lesson is going to be Graham's law of effusion. And effusion sounds a whole lot like diffusion, and there's some relation there, but it's not the same thing. And effusion is when a gas escapes through a narrow slit or a hole. And the example we're going to look at, we're going to have a balloon that's got both equal number of moles of O2 and H2 in it. And we're going to poke a hole in this balloon. So, and then we'll see that these gases are going to escape through that hole. That is what effusion is. Cool. Now, it turns out that Graham's law of effusion gives us a ratio of the rates of effusion. So the rate at which one gas effuses relative to the rate at which another gas effuses is equal to the square root of the ratio, the opposite ratio of the molar masses. And so what this ultimately comes down to the fact of 2 things. So one, the average kinetic energy of a gas is dependent only on its temperature. It's totally proportional to temperature. And so as long as these 2 gases have been in this balloon for a while together, then they're going to be at the same temperature, which means they're going to have the same average kinetic energy. And so I could say that the average kinetic energy for the O2 is equal to the average kinetic energy for the H2. They're equal. But just saying their kinetic energies are equal doesn't mean they have the same velocity. Now, kinetic energy is the energy of movement, of motion. It implies you have a velocity when you have kinetic energy, but having the same kinetic energy here doesn't mean that they actually are moving at the same velocity. And the idea is that, your kinetic energy is equal to 1/2 mv squared here. And so in this case, on the left-hand side, we have the mass of O2 and the velocity of the O2. On the right-hand side, the mass of the H2 and the velocity of the H2. And so kind of envision this for a second though. But if I take the same Volkswagen engine, and in one case I put it in a Volkswagen, and in the other case I put it in a semi-truck with a trailer loaded with goods. So both vehicles have the same engine, and it's going to have the same power output, and then be able to impart the same amount of energy to both the Volkswagen and the semi. But we know intuitively that they're not going to be moving the same speed. The semi, being so much larger, is going to be moving way slower, even though they might have the same energy output, so to speak. And so the same thing's going to hold true here, O2 and H2. So they might have the same kinetic energy, but O2 is way larger, and so on average is going to be moving much slower. Now, you got to be careful because, again, on average, they have exactly the same kinetic energy on average. But the average velocity, or RMS speed, like we talked about in the previous lesson, is going to be much slower for O2 than it is for H2. The heavier one slower, the lighter one faster. And as a result of the H2 molecules moving on average faster, they're going to make it out of the balloon faster. Cool. Now, if we kind of take a look at where this ends up, you could look at those those 1/2s as canceling, and you could take a look and get the velocity at which H2 is moving relative to that of O2 is moving squared, both squared, just move this one over, is going to equal the mass of the O2 mass relative to the mass of the H2. And you can see that to solve for the relative velocities, I just need to take a square root here. So, and it turns out that the rates of effusion are totally proportional to those velocities. And so you can take that ratio of the velocities and substitute it for the ratio of the rates of effusion instead. And so in our specific case, we want to know who's escaping faster and how many times faster. Well, it's the lighter one that escapes faster, so it's going to be the rate at which hydrogen escapes relative to the rate at which oxygen escapes. But the molar masses are going to have exact opposite ratio, so we're going to have O2 on top, H2 on bottom. Notice we're not actually going to solve for either rate of effusion. We're not going to actually know how fast either one is. We're just going to know this ratio. And the bigger this ratio is, the greater the greater the factor, if you will, the number of times faster that H2 is escaping relative to O2. And so in this case, we'll solve for that ratio, and we'll stick in the molar mass of O2 is 32 grams per mole, and the molar mass of H2 is 2 grams per mole, so don't forget both these are diatomic. 32 divided by 2 is 16, and the square root of 16 is 4. And so in this case, we see that the rate of effusion for H2 relative to O2 is 4, which means it's escaping 4 times faster. So it's 16 times lighter, but it's only escaping 4 times faster based on that square root relationship. So that's our relative rates of effusion. Now, if I said, what's the rate of effusion for hydrogen? You should just say, I don't know. And if I said, what's the rate of effusion for oxygen? You should say, I don't know. But if I say, what is the ratio of the rate of hydrogen to oxygen? You should say it's equal to 4. And that just means, again, the hydrogen's escaping 4 times faster.